Hello everybody and welcome to the NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 11 and in this lecture we will be looking into the MOSFET IV characteristics. In our previous lecture we were more interested in to understand the static behavior of MOSFET, which means that if you give a DC bias on the gate side and you did not apply any drain bias, then how does the MOSFET behave? And we came into the conclusion that there has to be some concepts of depletion layer, there has to be some concepts of inversion layer. We also saw how these capacitances in the inversion layer and in the depletion layer affect the overall characteristics of the device, but these were statics, which means that I am not assuming that any current is flowing through the device. Probably the first time here in this lecture series at least you are looking at the fact that if I apply a drain bias and let the charge flow from source to drain, what is the mechanism and what is the numerical analysis to that, and that is the reason this lecture has been added here. So, let us look at the outline of it. We have a MOSFET IV characteristics, we will be looking into it, threshold voltage, transconductance, and then finally CV characteristics, overall CV characteristics of the device. If possible, I will also show to you CV characteristics when the input frequency is relatively small and the input frequency is relatively high. This graph is a very basic graph. At this stage you do not have to worry about it. So, if you plot drain current versus gate voltage, right, this is a linear scale which you see, then what you will see is that as the gate voltage increases, most of the time the current is equal to 0. Beyond threshold voltage you will see that there is a substantial increase in the current, right. I will try to show you that. So, let me assume that. So, how do you find out? This is extrapolating it backwards, right. This is my threshold voltage. So, if I define this to be as my threshold voltage, then beyond this point there is an increase in the current. So, you do have a region of non-linearity here, and then this region is effectively a linear region of operation, and this is for various values of VDS. So, as the drain to source voltage increases, obviously the drain current also increases. Let us assume for the time being that my drain to source voltage is of the order of few milliamps, right. That is what we are looking into. Now, if I, and this is with the fact that your currents are, so in a MOSFET, if you remember, if you have an N-type MOSFET, electrons are the inversion layer, and if you apply a positive drain bias, they will be flowing in this direction, and therefore the conventional current is always in the opposite direction. This is the conventional current direction, right, and this is the electronic current, conventional current, and this is the electronic current, right. So, electronic current flows in the direction of the positive bias and conventional current flows opposite to the direction of the applied bias, for the reasons very well known to you. Two things you need to understand here, that therefore, as the drain to source voltage increases, the slope becomes larger, and therefore, I can say that the resistance offered by the channel also in fact reduces, right, offered by the channel reduces. So, which means that higher drain to source voltage will entail a lower drain voltage. I am giving a global picture of IDVG in drain versus gate. We will come to IDVD and IDVG in more details later on. So, takeaway from this slide is that the rise is exponential in nature. We have a region of non-linearity followed by a linearity, and most importantly from the point of view of MOSFET and from the point of view of cryogenic electronics, there is a threshold voltage above which you have a large current, and below which the current is approximately equals to 0. The last point is, for a larger value of VDS, since the slope increases, it primarily means that the resistance falls down, which means that for the same amount of voltage I get a larger amount of current, which you can see from here. See, if I draw a line like this, this is IDS1 and this is IDS2, this is IDS2 and this is IDS1. Obviously, IDS2 is larger than IDS1 for the same amount of VDS, right. This is the VGS, therefore, for the same gate voltage, but higher drain voltage which you see. So, though the drain voltage increases and you can see a current increase, but primarily that gives you an idea about the IDVG characteristics. Now, let me just come back to refresh your memory about from the previous lecture. So, if you remember in the previous lecture we were looking into the fact that when you have a space charge region, when you apply a gate bias, say you have an n-type enhancement mode MOSFET and you've applied a positive gate bias, but my gate bias is not that large enough to invert the channel. So let us say the gate bias is still positively very small, right? Then there will be a depletion region which will be created just below the silicon dioxide layer, and there will be a space charged region, and the space charged region width is given by formula shown here, right? Q times 4 epsilon phi fp upon q times n square root. What is phi fp? Phi fp is basically the difference between the Fermi level and the intrinsic level at silicon dioxide interface, and that is given by Vt, which is kT by q. This is kT by q, if you remember. This is in a thermal equivalent voltage, kT by q, ln of Na by Ni. So basically kT by q ln of Na by Ni. Na is the acceptor ion concentration and Ni is the intrinsic carrier concentration, which is fixed at T equals to 300 Kelvin. Now kT by q at 300 is approximately 25 millivolts, right? And that's what I have showed here. This is a standard value. I think it's always better, those who are working in this domain or those who want to work in this domain, that please remember that kT by q, which is thermal equivalent voltage at T equals to 300 Kelvin, is equals to 25 millivolts. And if you do natural log of therefore 10 to the power, because your Na was 10 to the power 16, which I inserted here, then Ni was 1.5 into 10 to the power 10, I got the value of phi fp to be equals to 3.3473 volts. You take this value of phi fp and place it in this expression xdt. Xdt is the width of the space charge, and if you place it and do some manipulation, mathematical manipulation, you get that the width of the space charge region is approximately 0.3 micrometer, which 0.3 micrometer, right? Why it is interesting to note is how does this value of x is being affected by the value of Na which you do. So let us suppose your Na value was very large, right? Let us assume that your Na value was 10 to the power 19, 20 or so on, so almost degeneracy is there. For the P, this is for the P type semiconductor, that is the reason Na. If it would have been an N type semiconductor, this would have been an Nd. Now if that would have been the case, your phi fp will be relatively large, right? And the reason is when you have large number of acceptor ions as in your substrate, you require a more amount of voltage to pull it up to form the channel. Now you see, which means that this phi fp will be large if your Na is also large, correct? So if a phi fp becomes large, you place this phi fp here, your xdt also becomes large, xdt increases, which means that in a sense you can predict that value, that as you go on increasing the value of the acceptor ion concentration, then you will automatically get a larger and larger amount of space charge in the depletion region. Please keep this concept in mind because we will be using it when we will be deriving the IDVD approach. Let us now come to deep dive into the MOSFET IV characteristics, right? And let us see how you can derive the IV characteristics of a MOSFET. So let us take up a bar of semiconductor which is placed on the, so if you see very carefully, this is the left side is the bar of a semiconductor, right? And then what we are assuming is that if the charge density within the bar is considered to be QD coulombs per meter, right? QD coulombs per meter, like one block of, so this one block consists of QD coulombs of charge, and the velocity is V, then we can say current is QD into V. Why QD into V? It is because the very basic definition of the current is that the number of charge carriers moving per unit area per unit time, right? That's how you define current. Now velocity is basically distance upon time, right? And QD is the volume charge density of the charge carrier. So when you multiply QD with V, you get the total amount of charges which have moved. So that's how I have shown on the right hand side that this block of charge, right, is moving from this point to this point. So this was initially this here, and then this block of charge together has moved to this particular block. So, if you want to determine how much amount of current is there, you just need to multiply QD with V, right, and then you can get the value of that. Said that, therefore, you need to calculate the value of QD, right. QD is the charge density, and that is what is written in the first point of the IV characteristics, that the IV characteristic tells me that we need to find the charge density QD in the inversion layer. So, I am assuming that the inversion layer has already been formed. So, initially you had accumulation, then you had depletion, then you had inversion. Inversion has already been formed, large number of carriers are already available. You see these negatively charged carriers are already available here in the inversion region, just below the silicon dioxide interface. Now, as I told you, for VGS greater than threshold voltage, any charge placed on the gate must be mirrored by the charge in the channel, because the electrical neutrality can never be violated. Why? Because see, technically what you are doing is you are applying a gate voltage. Now, since gate is having an oxide layer, there is no probability that there will be a current which will be flowing through the gate, but nonetheless there will be an electric field which will actually modulate the charge, right. But you cannot add or remove any charge from this whole system. So, the total charge density should remain the same, and that is the reason I have written that any charge placed on the gate must be mirrored by the charge in the channel, and therefore, they will give me a uniform charge density. How? It is given by this: QD is equal to W, the width of the charge, width of the channel, multiplied by Cox. Cox is oxide capacitance per unit area, multiplied by VGS minus VTH. Let us see what these charges are. Let us go one by one. Q, if you remember, is equals to, in this case, will be equals to sort of C into V, right. Now, if each C is the oxide capacitance Cox per unit width, let us suppose, then if you multiply with W, you get the total capacitance, and VGS minus VTH is also referred to as a overdrive. This is referred to as overdrive. Overdrive means the difference between the gate to source voltage and the threshold voltage is referred to as the overdrive, and this overdrive will become more and more as the gate voltage increasing. If I am assuming that the threshold voltage is almost constant, then VGS minus VTH is basically the over. The left hand side figure shows that the source and the drain are both grounded. It effectively means that there is no electric field in the longitudinal direction. Longitudinal means this direction. There is no electric field in this direction, but there is an electric field in this direction. In the transverse direction, there is an electric field. So, please keep that in mind while understanding this subject. Now, we go step by step and we increase the drain voltage VD, make it greater than 0. So, please understand, for all practical purposes, all my gate voltage and drain voltage is always extracted with respect to the source voltage. Source is generally grounded. So, we always find this to be as VGS and this to be as VDS, drain to source voltage, right. This methodology is basically known as the source bounded MOSFET, where we take each one of the nodes at gate and drain and we try to emulate it on the source side. Now, what I do, I made VD equals to 0, which means my drain voltage with respect to the source voltage is greater than 0. Now, the problem is, when you do that, the concept of resistance comes into picture. So, I have this channel, right, and I will explain it to you from the cartoon here. So, till now I was not applying any bias on the drain side and source side. Now, I am applying a bias on the drain side, right. I am applying a bias on the drain side, and this bias I am increasing in a step size, let us suppose by, or even let us not increase it, let me put a fixed bias of say 0.5 volts, whatever, and therefore, this is grounded, and therefore, this should be approximately at 0 volt and this point should be approximately at 0.5 volts. Why? Because this is N plus and this is also N plus. Their resistance are almost equals to 0, and therefore, there will be no drop of voltage across the source and drain region, right. I am also assuming in a very drastic manner that the contacts have also lost their resistances. So, therefore, the voltage drop from the contact through the drain source to this particular point is 0, and therefore, this is 0.5 is appearing here. If this is so, there will be an increase in the potential, right. So, this is 0 volts and this is 0.5. So, if you actually plot this thing, that this is my x is from this point to this point. So, x equals to 0 is my source end, x equals to L is my drain end, then it should be equal to 0, and then assuming that this channel is basically working as a resistor, I will have a voltage such that this goes to this particular point, this is 0.5, 0.5, and this is L, which means that at the source end the voltage is 0, at the drain end the voltage is equals to L, 0.5. If this is so, it effectively means that the effective voltage available at any point in the channel will be reduced by a factor of Vx. Why? Because it is a positive voltage, right, and therefore it will tend to reduce the effective voltage within the inversion layer, and that is the reason you see that my QDX now becomes W into Cox multiplied by. So, initially you had Vgs minus Vth already known to you, there will be an extra term which is coming, which is minus Vx, right. Now, why it is the minus Vx sign coming into picture? That means it is subtracted from gate to source voltage, let us assume, right. So, if you apply a gate to source, very simple, no, if you apply a gate to source voltage of 1 volt and the and you are moving from 0 to 0.5, right. So, if you applied a 1 volt here and you are moving from 0 to 0.5 here, then the effective voltage visible here will be 1 volt, here it will be, let us say, 1 minus 0.25, which is 0.75, and then you will have 1 minus 0.5, which will be a 0.5 here. So, the effective voltage which is visible to the electrons go on reducing as you move from source to drain, and that is the reason even negative Vx here and the threshold voltage is available here, and drain to is given by this. Now, this is for a fixed value of the drain to source voltage. If you increase that value, this Vx value will also go on increasing, right. That means, if it is rather than 0.5, if I make it 0.8, then within the same part of the channel the potential will be relatively high, and therefore, it means that charge density will be relatively small. So, higher the value of Vx, lower is the value of QD, charge density, right, depletion charge density. Now, let us look at the ID expression, therefore, that I multiply my QD with V with a negative sign, because the electrons are moving opposite to the direction of the electric field, and that is what is coming here. Therefore, V is equals to mu into N. You already know that the velocity of the charge carriers is mobility multiplied by electric field, and electric field is given by minus dV dx, right. So, if you put this into this, I get V equals to minus mu N times dV dx, right, dV dx, where V is the voltage and x is the distance along the channel. Now, if you put the value of QD and V in this expression, right, I get W into Cox into Vgs minus Vx minus Vth, which is coming from my charge equation, multiplied by mu N times dV dx, but that will be negative. Why? Because already I have taken negative, negative of negative will become positive, and therefore, you see it is positive x here. Now, as I discussed with you just now, that therefore, the voltage at source side will be equals to 0, and the voltage at the drain side should be exactly equals to Vds. Therefore, to solve this, so basically what you will do, this is basically a differential equation, solve it, you require two boundary conditions. One boundary condition is this one, and the second boundary condition is this one, and these are physics based boundary conditions. So, then what you do, you take dx to the left, cross multiply, so id dx, and you integrate from 0 to L, and you take this side and you integrate it from V equals to 0 to Vds. Once you integrate it and get the value, and then solving it, you will get this expression. That is important, right. Solving this, you will get this expression where ID is given as mu N C oxide W by L into Vgs minus Vth into Vds minus 1 by 2 Vds square. This is quite interesting. Look at this expression and make your Vds as small as possible. Say you say Vds equals to 0.01. Now we are in the process of deriving IDVD characteristics. So, let us suppose 0.01. So, if you multiply Vds square, it will be 0.01 multiplied by 0.01, right. So, 10 to the power minus 4 will be the answer. So, I can as well neglect this part, and therefore, ID and Vd will be almost linear with respect to each other. So, you see, if you look at this region where the Vds value is very, very small, and if you concentrate near the value at this point, these are all linear movement of ID, fine. So, if you plot with this expression, we get this. If you just take this expression, then as you start to make your voltage go higher and higher, the Vds terms becomes more dominant, and therefore, with a negative sign, you would expect to see And since this second term is a parabolic term, therefore you will see that beyond a particular point of VDS it will start going down, and that is what is shown here. You see, at any fixed value, do not worry what that value is at this stage, but at some value it might happen that this will exceed this value, and as a result the current will go down, not expected. So, we say that for VDS less than equals to VGS minus VTH, the device will operate either in the triode or linear region, and we define that expression. So, we divide the whole thing into two operations. One is the triode region and another is the saturation region, which will come later on. So, in the triode region I say that this is okay, I agree with you that this will be the final expression of ID, right. But in saturation, when VDS becomes exceed VGS minus VTH, when drain to source voltage exceeds the overdrive voltage, then we say that ID becomes equals to 1 by 2 into mu n C oxide W by L VGS square. Now, you see quite interestingly there is no VDS term coming in this picture, in this expression. That means the current is almost independent of the drain to source voltage, and that is what is drawn here. Just right, and that is what is and that is what is drawn here, right. So, you see they are perfectly parallel to VDS axis. So, if you plot sort of a profile here, these values are basically those points where VDS is exceeding VGS minus VTH. To give you an example, let us suppose this VGS is 0.5 volts, threshold voltage is say 0.2, VTH is 0.2, right. So, VGS minus VTH happens to be equals to 0.3. So, whenever my VDS exceeds 0.3 voltage, I enter into saturation. Am I correct? But if you reduce your VGS say to 0.4, then you see my VDS has to exceed 0.2 volts in order to get the saturation, and therefore, this point has shifted to the left. So, lower the VGS value, lower will be the value of VDS sat. This is known as saturation VDS, VDS sat saturation. These, let us suppose assume this point to be x, fine. At this place you have a current, which is current ID is not a function of VDS, fine. So, we will stop here today, and in this lecture at least. Just to recapitulate what we did, we tried to find out the IDVD characteristics of a MOSFET, explained to you the condition for triode region, linear, non-linear and saturation region, and finally, we looked into the IDVD characteristics of a MOSFET, right. That is what we are doing, and from the next lecture onwards, we will start doing the threshold voltage modeling. Thank you very much.